it is my absolute pleasure to introduce Saket Saurabh, who is a professor at Institute of Mathematical Sciences here in Chennai and also at University of Bergen, Norway. So he is a leading expert in the field of theoretical computer science, and his research mainly focuses on graph algorithms, parameterized algorithms, kernelization, and a lot other things like computational geometry. He is a recipient of Shanti Swarup Bhatnagar Prize from 2021 and ACM India Early Career Research Award. His work has been supported by both ERC Starting Grant and Consolidator Grant. He is an elected fellow of EATCS, Academia Europea, and the Indian Academy of Sciences. And I have known Saket for more than a decade now. So I think he is the reason I got into parameterized algorithm, he and Neil Dhara. And over to you, Saket. He's also my PhD advisor. Pause.
So he's the guy we should blame for you.
Yes.
Thanks a lot, Akansha, for your introduction. So, so today I'll tell you something about random walks and how to do FPT approximation. But I'll just give you a very simple example, keep it very simple till the last slide, which might be slightly this. So let me first start by congratulating Sweta for putting up this wonderful Center for Theoretical Computer Science. Hopefully we all can make use of and prove more theorems in local Chennai. So thank you, Sweta, for this. And with this, so let me tell you what problem I'm going to talk about. So throughout the talk, I'm just going to talk about this problem and design some 10 algorithms for this problem, giving you different set of things throughout. So the best way to explain anything, at least in parameterized algorithms, or for that matter, even in approximation algorithm, is you give this vertex cover example, right? So what is this vertex cover? So you are given an undirected graph G, your natural number K, and you are basically asking, can I delete K vertices so that what is left is independent set or does not have any edge? Or in other words, I want to find small set of vertices such that every edge at least intersects my selected vertices. So for example, here's my graph and you want to find vertex cover of size at most 3. So for example, if you look at this V1, V5, V3, then every edge has at least one endpoint in the selected set. So this is what will be my vertex cover. Okay? Any problem with the problem? So we all are there. Okay, good. So now let me give you the first FPT algorithm for vertex cover. I'm not going to define what it means by FPT and this. Yes? I will tell you. Don't worry. Right? I mean, I will define everything for you. It's just patience. Okay? I'm not going to use any big hammer, so, okay? So here's my algorithm, whatever that means. So what my algorithm does? Now, if you have an edge, you have to pick one of the endpoints. So I recursively try to find a solution which either picks U and try to find a solution of size K minus 1, drops the budget K minus 1, or from the other endpoint of my edge V and tries to recursively try to solve the problem on the budget K minus 1. So that's my algorithm. Okay? So this is a simple algorithm to solve my vertex cover. And of course I have some base case which says if K is less than 0 then return no, or if some edge is empty, some such base cases. But basically if you have an edge and you are looking to find a solution that contains at least one of the endpoint, so you try to find solution containing one and see if that leads to a solution. You try to find a solution leading to other and try to find a solution. If either of them succeeds, you succeed, else you fail. Okay? This is what is called FPT algorithm. Okay? Now what's the running time of this algorithm? So let's notice what happened to this algorithm. So I started with G and the budget K. In this search tree, I deleted U because I decided to put this vertex into my solution, and I'm looking to find a solution of size K minus 1, right, with budget K minus 1, similarly in the other side. Okay? So what is the depth of this tree? Depth of this tree is like K, K minus 1, and how many children each branch has? 2 children. So how many nodes this search tree has? Huh? That's it. So that's all that it is, and each node I'm going to spend some polynomial amount of time. So the total amount of time that I spend on finding this algorithm is like 2 power k some polynomial in n. Okay? So analysis is very simple. Every vertex cover S must contain at least one of n point, hence one of the two branches is always correct. Okay? So this gives a depth k search tree. You could have also written a recurrence, right? Why I showed you this, you could have written a recurrence that, look, I'm trying to solve a problem with budget k, and to solve that I'm trying to solve two problems with budget k minus 1. So that's this, and this polynomial, you know how to solve this recurrence. So from now onwards, I'm just going to forget this polynomial factor in this, just for the clarity, okay? So this is what is called vertex coverage FPT. So if you can get an algorithm with this k running like this, it's called FPT. Nothing more to know, nothing less to know. Anything else? Any question? No. Now, here's a simple principle for vertex cover that people have explored for last 3 decades is that, well, what is the meaning? There's another way of thinking of this. Look at any vertex and its neighbors. If you decide not to pick this vertex into the solution, what it means? Who will take care of these edges? This edge, or this edge. You better have to pick all these 3 vertices, right? And that is what is shown here. In the first one, I try to take this vertex into my solution. In the other one, I try to discard this vertex and take its neighbors, and we're done with it, okay? So, but now, let's look at what algorithm does this. Yes? No, that's a question we have to check, decide. You might be able to say there is no vertex cover of size at most k. For example, the example that I draw, if you try to find a vertex cover of size 2, you can say no. Or for example, if you're looking for a vertex cover of size 2 and you find a matching of size 3, what can you say? No, right? Because if you have matching of size 3, you have to pick one from each of them. So there are ways, it may not be always a yes instance. So it's like a decision question where your answer is either yes or no.
It's very suggestive, right? In the algorithm that you gave, the order in which you consider the edges did not matter.
Right.
But here, like, maybe smarter degree-based decisions.
Yes. And that's what we're going to do the next. Okay? So here's my algorithm, right? Imagine that if a graph has maximum degree 1, do you need to branch or do anything? What is this? It's like a matching edges and some isolated vertex. Solve it in polytime. Even if the degree would have been at most 2, you could have solved this problem in polytime because it is like cycles or paths. But what about if degree would have been 3? It's NP hard. So then you already have reached the hard case. But even like I do not want to go to 2 like this. So even if the degree is 2, I branch as he suggested. So I pick up a vertex with degree at least 2. And you are right. The best heuristic would have been to find a vertex with highest degree. For example, we know how to solve this problem with minimum degree 2 in polynomial time. Then ideal would have been to put degree v at least 3 and then I branch. But the reason I did not put it because I do not know how to analyze it yet in the settings that I need further. So I will leave it for now. Okay. So this is my algorithm. So now my algorithm is g comma k. My budget drops by k minus 1. In the other, budget drops by as much as degree, but at least 2 because the vertex that I'm branching on has degree at least 2. Now, if you write the recurrence, does it remind you of some recurrence? Fibonacci recurrence, right? So this solves to 1.618, right? So from 2 power k, we immediately went to 1.618 to the power k. So these are the 2 algorithms that you need to remember throughout this talk, and that's it, okay? Now, what is known for vertex cover? So let's know what is known for vertex cover. So people have designed an algorithm. I think if Nari is not in the room, then he's one of the co-author who has designed an algorithm for vertex cover who runs in time 1.25284 to the power k, okay, whatever. And vertex cover admits a 2-factor approximation algorithm in polynomial time. I will tell you in a minute. And we also know there's a hardness barrier that if you assume unique game conjecture, then you cannot do 2 minus epsilon. And if you believe p not equal to np, then I think root 2 or some such lower bound we still know. So the point what I'm trying to make you is that this is what we have known for vertex cover in FPT time. in 3 decades, and doesn't look like. Now, with people are pushing very hard and like breaking this 5 itself looks very difficult, hoping that someday we will achieve 1.19 algorithm looks even very difficult to do with the current set of methods. And we have such barrier in polynomial time. So what is the next question to ask? So in polynomial time, we have actually know what factor 2 approximation is best possible. So we just ask, is it possible that we can get 1 plus epsilon approximate solution? And I'm happy to run FPT algorithm, but you should beat this 1.25. So if I'm allowing you to get 1.1 approximation, maybe you should be 1.2. But if I'm allowing you 1.75, the running time should be different from 1 or 1.1 or 1.5 or 1.7. How do we do this? Okay. So can approximation buy us speed? Okay. Okay. So now I'll give you an FPT approximation for vertex cover. But when I say via, I want to introduce the definition. So what I mean by, so if you do classical polynomial time, the notion of approximation is very clear, right? There's a notion of minimum, and you are fighting against that minimum. So 2 times op, 3 times op, log n op, it's very clear. But in the world where we are going to measure the running time with respect to some number, I need to define what I mean by FPT approximation or this. And this is what it means. So I gave you this number k, okay? If you give me a solution of size alpha times k, I don't ask you any question. But when you say no, you are correctly concluding that the reason I failed is because there is no vertex cover of size at most k. The minimum vertex cover has size at least k. But when it says it returns you alpha times k, it doesn't mean that it has a vertex cover of size at most k. It could be that it has a vertex cover of size 2k and I returned you a vertex cover of size 2k. Or it has a vertex cover of size 3k by 2 and I returned you a vertex cover of size 2k. But when it returns no, you are correctly able to conclude that it is a no instance for vertex cover. But when it returns an answer, you are happy, you take this approximate solution and you don't ask question, as we do in the classical polynomial time algorithm. Okay? So this is what I mean by FPT approximation for vertex cover. And you can do this for any minimization problem. There's nothing about vertex cover. You either returns a solution of size at most alpha k, or you just say that optimum is more than the number you are trying to. And now why it is important, let me give you one very good example. Imagine a maximization problem. I want to maximize number of vertex disjoint cycles. It's an NP-hard problem. Now, at least k, and I put k equal to 2 or k equal to 3, but the number of vertex disjoint cycle could be as much as n by 3. So now, in polynomial time, we are trying to find too many vertex disjoint cycles, right? So this is why this k play a role. I don't care that you give me this or give me that. I am okay. Number of vertex disjoint cycle could be too many, but with respect to this k, if you are happily giving me something, I'm happy because that is how much computational running time I'm giving you or I'm providing you. Okay? So that is why we have to make this distinction. Maximization problems becomes slightly more harder to phrase, so we'll leave that discussion for later. But for minimization problem, it is fairly clean. I give you a number k and a factor alpha, which is an approximation. Either return me a solution of this, or you correctly conclude that the minimum size or optimum is more than the threshold you have provided. Okay? Any question on the definition? Yes?
So not larger than alpha k, it's larger than k.
Meaning? No. Yeah, just larger than k, not alpha k. Okay. So what is a simple polynomial time 2 approximation algorithm for vertex cover? You find a maximal matching and you return the both endpoints of this maximal matching. And you know that this is 2 times cardinality of m is 2 times the minimum vertex cover. You are happy because every matching you must contain at least one vertex in the vertex cover. Correct? So this is a factor 2 approximation. I'm going to modify this algorithm to give you an FPT approximation. How? It's very simple. Let m be a maximal matching. I'm going to give you 3 by 2 approximation. So what I do is that I find this maximal matching. I pick up any k by 2 edge of this, right? And take both endpoints of this. Okay? If the graph had a vertex cover of size k, whatever may be that vertex cover, which we do not see, must have picked one vertex from each of these k by 2 matching edges. So what is the remaining budget on G2? It should be k minus k by 2, right? Here, for this k by 2, to get this in polynomial time, to drop my optimum by k by 2, I have paid k by 2 times 2, so that's k. And on the remaining, I can run the best known FPT algorithm and give you a 3k by 2 approximation, right? So that's all this algorithm does, right? So it picks up this any k by 2 matching edges. And why it is important? Because this allows me to argue that opt has reduced in the reduced graph. Okay? Okay. So this is what happens, right? So 2 into k by 2, those matching edges, factor 2 approximation. And on this, I'm going to run my exact FPT algorithm. So approximation factor is guaranteed to be 3 by 2 times k. But what is the running time of this algorithm? Well, running time is you are running your expensive part, but on the budget k by 2. So if the best known algorithm is this, now it is k by 2, so this is the running time. So I'm getting a 1.5 approximation, but my running time is much, much faster than this. Okay? Now, there is no magic about 3k by 2. I could have done this for any 1 plus epsilon approximation, because all I need to do is I choose epsilon k by 2 matching edges, right? Then I pay epsilon k here, and my parameter drops here by 1 minus epsilon by k, right? So my running time will be how much? 1 minus epsilon by 2 times k, right? So this is my running time. So I can get any, so if you want to get closer to k, you are paying more and more running time. You want to get closer to 2, you are paying less and less running time, right? So just by playing on this, I have got this nice curve of running time. Okay? Any question? It could give you a good advantage. So people have designed very convoluted algorithm in last 15 years, but yeah. So for example, oh, let's find a triangle, 2 will be go into the solution. So let's take all the 3.
Instead of the exact on the right hand side, there you sort of recursively build this.
You could do that. At least for D heating set, for 3 heating set, people have done this kind of recursive. For vertex cover, I have more seen that people are analyzing local, and whenever they have opportunity to say that, oh, at least X will go and I have X plus 1 or X plus 2, pick all of them and paint this. So this is something which I have seen quite much more people doing it than recursive. But for 3 heating set, people have done recursive. But what I will tell you is that we can do way more faster than these things by interpreting these algorithms slightly differently. Okay? So what is the takeaway? So this is a curve that you are starting to get. Okay? So people up until now we used to design this algorithm, but now with this approximation, we are able to get plethora of these algorithms with different ratios. Okay? So now I will tell you, so now this was the starting of the kind of results people have studied, what is known in the literature, and what we are trying to provide in the current article. Okay? So it has witnessed a lot of growth in last decades, and people have proved, especially in the lower bound size, people have proved some amazing set of results by relating it to hardness of approximation in polynomial time, proving some variants of PCP kind of theorems for parameterized complexity, and proving, but this is still, people have not got the kind of results they still want, and this is a very active area, and people are working. So that is beyond that I can tell you. So what I'm going to tell you is what was known if you had C power k poly n algorithm, which in parameterized complexity we have plenty of them, can we get such kind of curve for those kind of problems, right? So we know how to solve them exactly. Can I get a curve for these problems by say, now I allow approximation, give me slightly better running time. So this kind of time ratio trade-offs. Okay? And this is what was known in the literature before us, is that people, everything was like more like a vertex cover or cousin of a vertex cover, except for feedback vertex set, which, so what I'm going to tell you is the ideas which we flushed out from this paper, this idea to complete totality in this article. Okay? So except this, everything was about cousins and brothers of the heating set. Okay. So the milestone in this area was by paper by Kluik and Shashanani and Fox 2020, who introduced randomized branching into this area of parameterized approximation. And they developed machinery to how to analyze these two variable probabilistic recurrences, and they applied it to this vertex cover 3 heating set, but still very simple kind of probabilistic recurrences. Okay, so more than the algorithm there, I would say their main contribution was that you can bring this machinery from convex optimization or information theory, type theory, and use this to solve some of these beautiful recurrences. Okay. So the natural question was that, I mean, how far we can push beyond this de-approximation? Like, which problems truly admit this kind of ratio? Can we systemize them? Can we automatize them? That look, if you have a branching algorithm which satisfies property A, B, C, D, then you have such a ratio algorithm. So that was the goal to design, is that if I have a problem for which we have classical branching algorithm that satisfies some properties, then I can automate it to design such time ratio trade-off algorithm. Okay? Because up until now, everything was completely by ad hoc. You pick a problem, you try to do like problem by problem, find some structure and do something. Okay? So our contribution is that what we do is we give you a formalized language for randomized branching rules and a meta algorithm that takes that if you have these branching rules, then this is the way we can automate, and that gives us many, many more examples than what we knew in the literature. Okay, so here are some examples, like some feedback vertex said, odd cycles, LP, matroid, this, that, everything can get. Okay, okay, so now, so what is our conceptual contribution is that now we are able to develop maths. For developing maths was that we had to go beyond whatever the framework of these people, but coming up with like the complex random walks, which are, some of them are quite counterintuitive, that even those can be used to design good algorithms, and I will tell you what I mean by counterintuitive. Okay, and measures, people always use these measures which were like K, solution size, but now we can analyze measures which are substantially different than just solution size. Okay, so all of these will look very, what is that called? Not very concrete, but I will make each of these lines concrete in the next few lectures. Okay, so now I'm going to take up my same example of vertex cover, and I'm going to give you approximation, but via random walks. So what will a random walk for me will mean? You are standing on a real line or integer line, standing at some place. With some probability you can go left, with some probability you can go right, and with some probability you can just stay put. Okay, and that's it. And what does random walk tries to analyze? That if I'm at some state and I want to reach to some final state in certain number of states, what is the probability that I can reach from some start state to some final state in these many steps? And that is all that the whole area of random walks try to understand, try to analyze. So what we are trying to do now is to take all these branching algorithms and try to map them to understanding some these kind of questions. So that is the goal. Our goal is to take most of these branching algorithms and tie them up of understanding some movement from some current state to some final state in some number of steps, and that's it. Okay. Okay, so let's do one such example, and it's funny. So this is the algorithm we had, right? We picked an edge. So now I randomize this process. Okay, I do not go into both parts of my algorithm. I randomly pick which of these endpoints I must pick into my solution. I delete from the graph and I recursively solve. What is the running time of this algorithm? It's polynomial, because I'm just doing k times of this. So what should be its success rate? Success ratio. If it would have been polynomial success, then it would have been like RP or these kind of algorithms. But here, because it is a polynomial time algorithm for an NP-hard problem, this is also called one-sided probabilistic polynomial time OPPs. Okay. So what is a success? So success is you fix a vertex cover S of size k, and at each round you are choosing an edge which has at least one endpoint in S. It could have both, and so probability that you will hit that endpoint is with half, because I'm just doing a coin toss. If it comes head, I pick Q. If it comes tail, I pick V. That's it. So probability of success is at least half to the power k, and that's it. So this is my algorithm which we did before. Now I am just doing this in a randomized way. Now what does it provide us? So now I can think of this algorithm as a random walk view. Okay, what is this? I start at k. So what I am going to tell, up until now, how many vertices of S still need to be discovered, right? So that's my state. Every time if I do correctly, then I move from k to k minus 1 because I have discovered one vertices of S, so I have moved. So basically, if you want to understand the probability of reaching 0 in a bounded number of steps, and that's it. So now let's ask this. If I ask k steps, what is the probability? 3k by 2 steps, what is the probability? 2k steps, what is the probability? Okay? So now what is the probability here? Notice that if you make a mistake, it's a vertex cover. So whatever is remaining still remains to vertex cover. So you stay put, you never go left or right, because vertex cover, you don't go left. Vertex cover does not increase if you made a mistake. It can only decrease or you can stay put. So this random walk stay puts with probability at most half, and it goes forward with probability at least half. Why? Because both endpoint could be in the solution. So in that case, you would have moved with probability 1, right? So that is why it is at least half and it is at most half. Okay? Okay. So this is all that it is. So this is my random walk. And now, and I want to understand, to reach 0 in exactly k step, the walk must decrease in every step. And this is what we got half to the power k. So we have got our classical vertex cover algorithm in this random walk way. Okay? Let's run this for 2k steps now. Now I'm running this algorithm for 2k steps. It means all you care about that at least k times you should move left, and other k times you can just stay put. So what is a probability of starting from here, spend some time drinking tea, maybe you felt hungry, you like sleep, right? So this is like, I call it like, this we study the tortoise and hare. So like in this process, hare always wins, tortoise can still go slow, okay? So what is this? So let x be the number of steps that move the walk towards 0 among the first 2k steps. So you can think of this that you are doing 2k coin tosses. How many times you will, what is the probability you will get k heads among this 2k? Because every time head happens, you go left, right? So this is nothing but binomial. This is binomial n comma p, where n is 2k, number of coin tosses, and p is half. It just happens to be half. So that's your factor 2 approximation algorithm running in polynomial time. Okay? So if I did 3k by 2 steps, it's the same thing. Now, but number of coin tosses that I'm doing is 3k by 2. So if you do this maths, you get this number. Okay? So the probability of success is like this. So if you want to boost the success probability to constant, you do just normal independent amplification, 1 by this. So it is 1.0887 to the power k, right? So which is much, much better than what we got from that matching idea. Okay? But the caveat is that was a deterministic algorithm, this is a randomized algorithm, and we all don't know how to de-randomize this random walks based algorithm yet. Okay? So the random walk view already improves the running time. Okay? So this is already very encouraging that if we are able to move these branching algorithms to some first randomized good algorithms, understand their behavior as walk on some plane or this and that, we can take advantage of that to design good algorithms. Okay, so that's a key step. Okay, so that was so what I mean by monotone walk. So I call a walk monotone. If every step, either you stay put or you go towards your target. So vertex cover walk was so far monotone. Okay. And we also saw this algorithm, remember, where what we tried to do, we did not branch on an edge, we branched on a vertex. In one side we put this vertex, in the other case you picked up two vertices of this, right? But now notice, still this walk is monotone, because by adding vertices to your vertex cover, you are never going to make vertex cover bigger, but there is a jump, right? It's possible that if you are branching on a vertex cover of size, like neighbor of size d, and if you correctly decide it, you can jump to I minus d, right? So that's all that is happening. So with, if I do the same with probability half and half, I'm not going to get, so let's decide what probability we should jump. So I go to the next step with probability p, I do this jump step with probability 1 minus p, okay, starting at k, and I'm asking the same set of questions, right? In this jumped random walk, what is the probability that I can go from starting state to final state in some number of steps, and that's it.
You know, be careful, right? Like earlier, the number of steps told you the end, like 3k by 2 meant you were.
Correct.
If you pick the degree, like the cost.
Right. So we'll get into troubles. We'll soothe, and that is where all the magic starts. Okay. So, wait. Okay, right. So this walk is still monotone in the definition we came, but it is no longer unit step. Okay. So let's first analyze this. Let's just get the classical branching algorithm, which was 1.618. How do you set this probability, right? So you can set phi equal to 1 plus root phi by 2. It's not that I came up with this number magically. You just put this p, 1 minus p, you try to boost, like try to see what is the best, and you will get this number, right? And what is 1 by phi? So 1 minus p is nothing but 1 by phi square, okay? Now since every jump decreases state by at least 2, this choice will be enough to prove the success probability is at least phi minus k. And now let me give you proof why the success probability is phi minus k. Okay. So how many A steps you take? Suppose you go 1 A steps and you take B many jump steps. So what you know, A plus 2B is at most k, because every time you take a jump state, the parameter drops by 2. Okay. So what is the probability of following this path? So 1 by phi to the power A, 1 by phi squared to the power b, which is 1 by phi a plus 2 power b, which is 1 power phi power k, and that's it. Right? So one run succeeds with probability phi to the power minus k. Okay? So far, so good. Okay? Anything here? So if you notice, we got this 1.618 to the power k when we were doing this branching. You actually can recover the same thing. It is basically, if you think of this, you are just sampling the leaf of this search tree, and that's it. So it's just basically a way to sample a leaf of this search tree, and that's it. And that is why you get this. So if you had very complex branching algorithm, you can set up these probabilities in a way that you will recover the same number. Okay? Okay, so this is all that I said. Now let's go back to what Siddharth was saying. But what are the set of difficulties that this random walk faces? In the exact algorithm, successful path always needs to move this side. But if I allow you to stay, right? If I allow you to stay, but what is the meaning of stay, right? So notice, now you should have picked up V, that's a right move, but you decided to pick all of this n of V. Now imagine that this degree was like k by 2 and you were hoping to get 1.1 approximation. You deleted k by 2 vertices from the graph already and your optimum did not decrease. So even if you, after this move, if you are running correctly, you are still going to give me 3k by 2 approximation. 1.1 is not possible. So this move is not correct. Okay? So previous mistakes were unit cost. But now single bad jump can kill your algorithm. Okay? So we need much more refined and controlled process than this. Okay? So let me design a different branching algorithm which achieves 1.618, and we will implement that. Right. And that's what I'm going to do now. Okay? So I'm going to modify my branching algorithm, which, okay? So rather than degree, I fix two vertices and I say in the one branch I'm going to pick this, in the other branch I'm going to pick these two vertices into my solution. And why this is correct, like look at S any vertex cover. If V is in S, then the first branch is compatible. In the second branch, V is not in solution, then all the neighbors go into the solution. So in particular, these two vertices go into the solution. This is perfectly fine. If you analyze this algorithm, this is also going to give to 1.618 to the power k. But what happens now is, let's look at the choices now we make. So suppose this is what optimum choices are and this is what our choices are. So if optimum also picks V, V also pick V, then op decreases by 1, error is 0. But optimum picks V and B picked XY, op did not drop, but error has increased by +2. And similarly you can do here. But if we would have branched on that degree, my error term would have been that much and then we would not have been able to control. So now with this slightly modified algorithm, we are able to capture that a wrong choice only contribute at most 2 to the additive error. Okay, any question? Okay, now coming to him, I cannot just count number of times I make a mistake because different mistakes cost different, right? So if I was planning to pick V and I picked XY, my cost was 2. I was planning to pick XY, I picked V, my cost is 1, right? So now, before just knowing number of bad moves was good enough for me to analyze an algorithm, but now I not only need to know number of bad moves, but how this bad move affects my error calculation, I also need to keep track of those two, okay? So now you see the difficulty. So you start to analyze more and more complex algorithm and you start to get more and more complex things that you need to keep track during your algorithm, okay? Okay, so suppose I wanted to ask for 3/2 approximation, then what I'm asking, you output a vertex cover of size at most 3/2k, given that g comma kgs is. That is what I'm interested in, that if this random walk is there, right? I don't know, now I don't even know to think about number of steps because number of steps doesn't correspond to the size of the solution. I can run small number of steps and still have lot much more error. I can run for long number of times. So I am not able to keep track of just formulate even these questions properly in this, oh, I want to go from starting point to this in these many steps. I'm not able to formulate these questions also properly, right? Okay, so I know for sure that this is better than 5 to the power minus k. Why? Because everything that goes always left, left, left is counted here, but there are many more paths that are there. So how to account? So I definitely know intuitively that success probability is at least this much, but how much it is? Okay. So now to do this, state has now 2 coordinates. K tracks the remaining parameter and B tracks the remaining additive error budget. Okay. Okay. So now our walk is no longer one-dimensional because now it is a walk over z square, and I am not able to analyze these 2-dimensional random walks because I do not have clear picture of what I mean by number of steps, what I mean the number of paths, right? So rather than doing this, we study equivalent probabilistic recurrence that describe the behavior of this walk. Okay. So now we will have PBK, which denotes the worst case success probability when K is the remaining parameter, B is the remaining additive error budget. Okay. So what you write this is what you will write. Okay. Now notice, so let me explain to you this recurrence. If V is in my solution, right, and you got head, right? then what happens? Your budget for the error has not changed. Your optimum has changed with probability 1 over 5. But I could have also made a mistake, right? But if I had made a mistake, I would have picked up both of its neighbor into my solution. So amount of error I allow you in your algorithm has decreased by 2. So the budget of error has decreased by 2, but your opt has not decreased. Okay? Or I could be in the other case where V is not in opt, then I should have picking both of its neighbor, but I decide to pick V into my solution. My budget of error has decreased, but my opt has not decreased with this probability. And in the other, I am not putting to the error. So B remains the same, and this decreases to K minus 2. Right? So this is how set up this recurrence. Okay? Any question on this recurrence? So I have to take minimum of these two because I really do not know what is the reality of the algorithm. We tried, but it doesn't give us number. It is much more useful to prove convergence and this kind of thing. But we needed how fast it converges, and we need quantitative bound for that. And that became slightly more difficult. Okay? So analyzing the behavior of such recurrence was already far from straightforward, and this is what this paper in Kulik and Shasnani did to some extent. Okay? And now, so there are some two counterintuitive. So second parameter may increase rather than decrease. Okay? So what I mean, up until now, we have always seen that we always go left or we stand. But there are lots of algorithms where if we do, I can actually increase my solution. Or not the solution, but the measure by which we are trying to analyze the algorithm. It can increase. And I will give you a concrete example. And that is very counterintuitive, that why will such algorithms will go and even give you good running time. Okay? So that's a counterintuitive. Now, as you notice that for vertex cover, it was easy that if I go a vertex and if the choice for approximation is bad, then we were found an easy way, just pick two of them. But for many problems, you cannot find this. So use like if you go there, it's like a kill state. So you can imagine that you're going from India to Pakistan, like not in a proper way, and there are lots of, what is that called? Mines are kept, and you still have, but there's still a lot of paths. Right? This is what my kill state does, right? That if you reach there, you're dead. You cannot recover from there, right? So we wanted to have, because for many problems, we did not find any simple way to make this approximation easier. But we said if you go there, like you are dead. Even then there are enough paths around that gives you good probability of success, and you can get very good running time for these algorithms. So we try to include a kill state. It's like if you go there, you can imagine that there's an integer line and there are some points where the black you cannot, so you have to jump over it. But still there are enough paths. Okay? Okay, so let me go towards the general model now. So, okay? So how we encode a branching rule? So now, to check the behavior of these algorithms, we have two matrices, what is called additive error incurred while lifting a solution back, and T is how does this drop change it. So now we keep track of these two things by these two matrices. And I'll give you an example what the entries of these two matrices will be. Okay? So for example, look at this branching algorithm where you picked V and where you picked U1 and U2. Okay? Now what are these row corresponds to? Row corresponds to V being in opt. Right? So look at if V is in opt and you decided correctly, then the error is 0. But if you decided wrongly, then the error is 2. Similarly, in the other branch, if you decided that both should be in the solution, but you decide to pick V, error is 1 and this. And this shows change in measure. Okay. So all we are trying to tell is that what I mean by this. So my algorithm is that I don't care about what your algorithms are. what your branching algorithm is. You give me B and T matrices, I know how to optimize this. Okay? So that is where all the things. So what will I ask from the user? I don't know what algorithm you're designing, for which problem you're designing, I absolutely don't care. You give me your B and T matrices, and then I know to design an algorithm which will optimize corresponding to this. Okay? So that is how we try to encode the generality of all these problems into these matrices. Okay? Any question? You think of this way, right? What is my algorithm doing? So rows are how rows think of, so we had this matrix, right? Which rows were what optimum does and the columns were what does algorithm does. So suppose that first row is I also decide to pick V into the solution and algorithm also, opt also decides to V into solution, then the error is 0. But here I decide to put the correct choice should have been V, but your algorithm picks both of the endpoints, then your error is 2. Okay.
So when you say designing algorithm, what probability do you choose those?
What? No, you will have to give me B and T. Okay, I will come up with my probabilities which will optimize everything. Like I will come up with a distribution given B and T which will optimize these things. Okay, so you will just give me B and T. You will not give me the distribution.
There are like, you could have, like at least the vertex, for example, suggest that you could have chosen these a bit better, but probably that doesn't lead to a better.
What?
Like higher degree, when the graph itself has higher degree or
Yeah, you can branch like 1 and 3. Like we could do 1 and 3 because we know how to do 1 and 2, then this like 1 and 3 doesn't matter. So you're right. So we could do those things. Okay? Right. So it just tells you that if you had 10 branching rules, then you will have that many rows and columns, right? Rows because, columns. Rows are basically what are the real states of possible these algorithms are, and columns, what are the choices this algorithms makes. Okay? And for each rule, you will have different matrices. So each rule only tells us if this rule, this is an B and T matrix. If different branching rule, there will be different B. So you give me all this B and T matrices, and then I will optimize it based on that. Okay. So what I mean by monotone case, now in this definition, if all the entry of my measure matrix is at least 0, then I will call this walk monotone. So now let me give you one example of non-monotone walk. Okay. So this is something which people have studied quite a lot in parameterized complexity. It's still a vertex cover problem, but how do we analyze its running time is slightly different. So let me first define the measure by which we want to have a running time. So what is a running time? So lambda g is the cost of, if you write the classical LP, linear programming for vertex cover, its cost. Now we know that any integer linear programming has value at least linear programming, LP. So I'm saying my measure is opt minus the lambda g. This is why it is also called above guarantee, because the value of LP provides a natural lower bound on the size of the solution. Okay. So you are still finding a vertex cover, but you are not allowed to measure the running time as a function of k, but as a function of this parameter, right? And that is what FPT is all about. So you have a different same problem. You can come up with a different measures, different way to analyze, and different analysis could give you a different algorithm. And why it was interesting for all of us, because we know it's a FPT parameterized by solution size. Can we show its FPT parameter is something even smaller, right? So if the way you show hardness, so you're not happy with NP hard on general graph, then you try to find it's an NP hard on planar graph of maximum degree 5. So in the same spirit, we try to do here. If it is FPT, what is the limit by which we can show FPT? If it is hard, what is the largest parameter for which we can show it's hard? Okay, so this is what it is. Now, I'll give you a situation. Okay, so here are the standard branching rules, processing rules. LP has all unique half optimum solution, and the graph has minimum degree at least 3. So you can do all this pre-processing and get here. And after that, algorithm is exactly the same that what I told you. You find a vertex, pick up its degree 2, in one branch you delete, in other branch you do U1, U2, and that's it. And that's an algorithm which gives you an algorithm with respect to this parameter. So you can analyze the same algorithm with this new measure, but all you care about is that you do pre-processing to get to these places. And this is very standard in, it has known in approximation world for decades that it has all half unique solution. Okay? Now, let's look at a wrong case. Suppose V is in optimum, but we decide to take U1, U2. Now, opt doesn't change it, but your lambda can only decrease by 1. Because everybody had half, you deleted 2 vertices, so lambda will just drop by half. But let's compute mu of G2. 2 times opt of G2 minus lambda of G2. If you do this math, you will get mu G plus 2. So now what happened? I started with a graph which was less complex. I have gone to a graph which is more complex. Okay? So we thought for a long time that these kind of walks cannot be analyzed. But if you see Soning's, he goes left, right, wherever he goes, and he's able to analyze. So if we have a boundary that I don't care where you go, you take a round turn and come back. You will still reach home, right? It's just that more far you go, more you will have to pay. But less far you go, you can still come back. You don't have to just stay put. You can go left, right. Ultimately, if you go here, as many times this, if we are able to calculate this, that's your approximation factor. And that's it. Okay? So if you write down the matrix for this, this becomes now negative because my measure for the graph has changed. Like it has increased, it has not decreased. So these are like non-monotone matrices. Okay? So a wrong move may increase the measure and the walk is no longer monotone. This we didn't know how to analyze for a long, long time. And this maths makes life way more harder because a lot of theorems in convex optimization that we use for monotone is no more applicable. So you have to put some upper bound and this and that. It works, but it was a long tour. It was not, we couldn't use direct off the shore lemmas from the book. So we had to prove our own lemmas for these things. So that's the basic difficulty. I mean, computationally we knew that it works by coding. So we knew that it works, but we didn't have math for 1.5 years to tell people that this works. So that is where all the magic, like numerically we knew that this works because you code, you put this and you can check. But nobody is going, this is a heuristic. We had to do maths. Okay. So if you write down these states, now it can look like all kind of places. All kind of places these paths can go, but that's perfectly happy because I can write my recurrences. I can still write my recurrences. Now notice, what does this tells us? It was, oh, I am correct. If I'm correct, so this is like gamma 1. This is what, I do not know this probability. This is what, you give me the matrix, I will write this recurrence, gamma 1. This is my distribution, which my algorithm will optimize. So here if you notice, it just tells that, well, my measure here has decreased by 1. But look at here, it has increased by plus 2. But my error has decreased by 2. Similarly here. So, and you have some boundary condition. So this is the most general form of, one general form of recurrences that we were able to solve. And also let me tell you, we do not know how to solve these things when B is any arbitrary number. If B is some function of alpha times measure, only then we are able to analyze it. Which is good enough for our purposes, but if someone needs to do something different, he or she will have to do something very different. Okay, so in last 5 minutes, let me.
Negativity allows you to also analyze algorithms where you sort of don't revoke your decisions.
Yes.
You put back vertices that you're selecting.
Yeah, it allows us to do so. So there's one problem for which we had to do this, otherwise we could not show anything. But for some problem we couldn't do, and that is why we need to put kill. Like if you increase so much, like there's absolutely no way you can come back. So those are kill states. because we couldn't bound, once you go to this stage, we couldn't bound any approximation factor in any reasonable way. Okay? Okay, so what is our general framework? So what we define this Oracle subset problems. So there are some pre-processing rules, those should be exact. We believe that this can be made lossy, but we do not know yet. Branching rules of constantarity means like you branch in 3, 4, 10 ways, not in infinite ways. Major mu that tracks progress, and you can have an Oracle access when needed. And why did we need Oracle access? Because now that we are working with LP and this and that, sometimes we need to know whether it is feasible, what is its solution, these kind of things. So that is what I mean by Oracle access when needed. Okay? So this is what I mean by Oracle subset problems. Equipped with exact pre-processing rules, they should not be lossy for now. Branching rules of constantarity and major mu that tracks progress. Okay? And what the framework needs, you have to give me the problem and the measure, the pre-processing and the branching rules, and the local signature matrices B and T for each branching. That's all that I need from you. And almost all the classical branching algorithms that we are aware of can be encoded in this uniform language. And what we show is that if an Oracle subset problem which admits C power mu deterministic algorithm and has a proper set of branching rules, like this kind of branching rules that I told you, like B, T matrices, I can write all this, then for every target approximation factor, turns these branching rules into randomized FPT approximation algorithm, and branching probability are chosen like automatically. You don't have to give me, this is a job of us, and they are optimized to give you best running time by the framework. Okay? And so you get all these problems, and this is what was known in polynomial time approximation and what we are able to get in this table. Okay? So let me conclude in next 1 or 2 slides. So what we did, we revisited vertex cover as running example for FPT and gave you FPT approximation, interpreted branching algorithms through the lens of random walks, monotone to non-monotone, developed a general framework turning suitable branching rules into this time approximation ratios. And what remains open? I don't know whether it can be applied to other problems like directed feedback vertex head, planar vertex cover, I don't know. Can be extended to even more richer works, but more importantly, which at least I have, it has at least bothered me a lot, can we get deterministic version of these algorithms? We have absolutely no single deterministic algorithm for either of these problems yet. So that remains in my head one of the biggest open question. And thank you. Any question?
Okay, so since we are slightly out of time, maybe we can take the questions offline. Thank
Okay.
you, Saket, for the talk. And we
Thank you. Thank you.